Okay, hello Cloud Gurus. Welcome to the networking module. The blueprint introduced in October 2018 includes some new and interesting things around networking. No longer is it focused just specifically on the discipline of networking, but using networks in the context of large complex organizations. So in this module, we're going to be covering parts of 1.2. And then we're also going to be walking through some design tips for new solutions and existing solutions. And because often networking is involved in the migration or the process of migrating from on-prem to the cloud, we're going to touch on some of these aspects as well. So let's get started. Let's start off our concepts with just a little Amazon networking refresher. Now, you should already know the physical layouts of an AZ and the region concept. You should know what a VPC is and how to create one. You should be able to create private and public subnets and know what the difference is between the two. You should know what NAT is and what disable source destination checks mean. You should know what a routing table is and some basic routing terminology like default routes and local routes. You should really know your IPv4 addressing and subnet mask notation. So /16 should mean something to you and /24, and you should know what that means in terms of a net mask. For the exam, don't worry too much about IPv6, but you really should know IPv4. And you should also know some intermediate networking terminology like what a MAC address is, what a port is. You should know the difference between a gateway and a router. So you hungry yet? I sure do love me some pizza. And feel free to go grab something to eat while you're watching this chapter. If you don't have much of a background in networking, this might be a pretty challenging chapter, so your brain could probably use some extra energy. And the objective isn't to make you a network engineer, but just to give you enough vocabulary and concepts that the AWS networking features make sense. And remember, we seek first to understand, then apply. Speaking of understanding first, I'm going to introduce you to something that has really helped me, and that's the OSI model. If you want to really impress your network engineering buddies, learn the OSI model. Way back when I was studying for my very first certification, the coveted, at least at that time, it was coveted, Certified Novell Engineer, I had to learn the OSI model. And it describes how to think about network operations. If one layer has a problem, then your message isn't going to get through. Your web browser is not going to receive that web page, or that ill-advised tweet after a night of partying never goes out. It's also quite helpful in troubleshooting networking and application problems. I use it as sort of a mental checklist when my network isn't working quite the way I want to. And so it starts at the very bottom. That's the physical layer. That's the copper or the fiber optic cable that carries the signals. Now we have the data layer, and that's the MAC address layer. That's the layer of your network card, and the hardware of that network card is assigned its MAC address, which is its unique identifier. And we have layer 3, which is the network layer. And generally protocols like IP or IPX or ARP live on this layer. Then we have the transport layer. This is where TCP lives. The session layer, we have the presentation layer, and ultimately we have the web browser at the application layer. And that interprets the messages coming across in the HTTP protocol and renders that as HTML so you can see the web page. The reason I had a pizza on the previous screen is because there's this mnemonic that helped me remember the layers of the OSI model. And I still remember it to this day. It's please do not throw sausage pizza away. Now, the reason I have a yellow line here between layers 2 and 3 are that that's kind of a general point of demarcation between what AWS's responsibility is and what our customer responsibility is. So if you recall from earlier study on AWS, a commonly used term is the shared responsibility model. And in networking terms, the line between customer responsibility and AWS responsibility lies somewhere around the border between layer 2 and layer 3. I say around because there are some cases where both the customer and AWS have the ability to reach across that line. Now, your EC2 instances do have access to virtual items that would normally live at layer 1 and layer 2. An Elastic Network Interface is an example of such a thing, but it's not a physical network card. It's a virtual card that lives in software. And since AWS is a multi-tenant system, they have to be sure that customers can't negatively impact other customers where they're sharing that same physical layer. And so AWS has imparted certain limitations and restrictions. One of the limitations that AWS and most other cloud providers enact is to not allow multicast. Now let's take a look at the difference between unicast and multicast. Unicast is like a phone call to someone. You dial the phone number, and when the other party answers, you can have a conversation and it doesn't much bother anyone else on the network. Think about it as like a direct conversation between two people. That's what unicast is. Now, multicast, on the other hand, is like somebody shouting over a loudspeaker to everyone. Kind of like that scene in the classic Blues Brothers movies where they're driving through the neighborhoods with that loudspeaker strapped to their car, advertising their blues show that night. And this is why AWS doesn't allow multicast. You see, multicast is when a network card starts sending messages to everybody on the network. And because this is done at the MAC address level, it's a layer 2 activity. So if AWS allowed multicast, then it could negatively impact other customers' network activities as well. So a key thing to remember here is that multicast just doesn't fly on VPC officially. Now, there are some third parties that have come up with workarounds, but in the context of the exam, multicast isn't supported. Let's take a look at the differences between protocols. And you're probably going to get asked some questions on the exam regarding these protocols. First, we have TCP. And TCP is known as a connection-based stateful protocol, and it acknowledges receipt. So in plain speak, after everything I say, I want you to confirm that you received it. In contrast, UDP is connectionless and stateless. The plain speak version of that is, I'm going to start talking, and it's okay if you miss some words. UDP is used in streaming media applications and also in DNS, mainly in DNS because it's very simple, and streaming applications because it doesn't require an acknowledgement for every packet of information sent. Now, ICMP is kind of like the metadata language of the network. It's generally used by network devices to exchange information. And in plain speak, it would be something like, we routers can keep in touch about the health of our network using our own language. And ICMP is used in commands like a traceroute or a ping. Let's move on to ephemeral ports. So ephemeral ports are these short-lived transport protocol ports that are used in IP communications. And they generally exist above what's considered the well-known IP ports, meaning above 1024. And they're also sometimes called dynamic ports. And the suggested range for them to live in is between 49.152 and 655.35, but different OSs have different default settings for ephemeral ports. So be sure to double check your OS for whatever the default ephemeral ports are. Now, they definitely have some NACL and security group implications. And so let's look at how ephemeral ports work and why they work. And I think you can see why they do have these implications on our security groups and NACLs. Now, this is a quite simplified example, but this is just to give you an idea of the type of conversation that goes on. And in this case, we're using TCP. So there's a connection that's made, and there's also some TTL, time to live, that we're going to have to keep in mind as well. And this concept will come into play more prominently when we start talking about elastic load balancers and something called sticky sessions. So in this case, let's just say we have a web server here that's on the left. It's just hanging out, listening to port 80. And then we have a client. And that client dials up the IP address of the web server. And it says, hey, I'm client 6, and use port 56784 to respond to me. So this is an important concept because the client is in charge of defining the ephemeral port that the server should talk back to on. And so the server says, hello, this is server. Nice to meet you, client 6. Here is your web page, and I'll keep a session open for you, and it's going to respond back using port 56784. And the client says, thank you, sir. So it acknowledges that it received that message. Remember, we're talking TCP here, so there's an acknowledgement. Then some time goes by, and the client says, here's another web page, and it's going to communicate on port 80. And the server says, hey, I know you. I'm going to use the existing session that I already have open. And because I already have that session open, I know that you like to be communicated on 56784. And of course, the client says, thank you very much. Now let's look at an example that uses both TCP and UDP. So the same scenario happens. The client says, hey, I'm client 6, use port 56784. And let's say in this case, the client is requesting a media file and it uses UDP for streaming that media file. So the server says, hello server, nice to meet you client 6. Here's the video stream that you requested. And it's using UDP port 56784. And the client doesn't say anything. It just gobbles up the data. And the server sends more. And the client just keeps gobbling up that data. And the server sends more and so on. And so this is a demonstration of the difference between TCP and UDP. UDP is just send, and the client just consumes it. This is why UDP is favored when we're talking about streaming media, because you can see if you're sending a lot of data, having to acknowledge each and every packet of that data could get very burdensome on the network and on the client and on the server and so forth. So this is how we use UDP. Now, I also wanted to talk about the reserved IP addresses in AWS VPCs. And there are 5 reserved IP addresses that you just can't use. Now, in this case, we're using a subnet of 10.0.0.0/24. So in that particular subnet, the addresses we can't use would be the 0 subnet, that's our network address, the 1 address, which is reserved for the VPC router, the 2 address, which is reserved for the AWS DNS, and 3, which is reserved for some future use that AWS doesn't know yet. And finally, we have the broadcast address, which we can't use as a valid IP address either. Now, keep in mind that it's not these specific numbers that are reserved, rather it's the sequence or the placement in the IP range. So if we look at a different CEDAR block or CIDR block for you purists, the network address in that case is 16. And that would mean 17, 18, and 19 are unusable for us. And in this case, 31 is the broadcast address of this particular subnet. So when you're architecting your subnets and your VPCs, make sure that you use some ranges that have enough IP addresses that you can account for these addresses that you're unable to use. Now, just a brief note here, something that maybe some people aren't aware of, but the physical to logical assignments of an AZ is done at the account level. So in other words, when your account gets created, the physical availability zones are assigned to their logical names. And that means your US West 2A may be a different physical AZ than another account's US West 2A. And so why does AWS do this? Well, really to balance the load across its data centers. If you're creating a new instance, you're probably going to naturally lean towards dropping that in availability zone A, for example, either consciously or subconsciously. And so by randomly distributing how the logical names line up with their physical counterparts, Amazon hopes to distribute the load there equally. There's a bit of a security angle here too. Let's say you wanted to do harm to a company and you happen to know that that company stored their data in US West 2A. Well, you could go and do something bad to US West 2A if you knew that that US West 2A equated to one and only one physical address. Now, Amazon doesn't publish the exact addresses of their data centers, but I imagine in the communities they exist, they probably stand out a little bit. But using this round robin distribution, even if you knew that a company stored their data in US West 2A, you'd basically have a 1 in 3 chance of guessing correctly. In 2016, I attended AWS reInvent for the very first time, and it was a career-changing event for me. But maybe more on that later. One of the talks was given by James Hamilton, who's a VP and distinguished engineer at AWS, and his talk was on the inner workings of the Amazon network. It was amazing. If you have 30 minutes, I promise you'll be amazed as well at the level of engineering, technology, and the effort AWS has and continues to invest in the platform. In this module, we're going to talk about how to connect your on-premise network to your VPC. We're going to talk about a managed VPN option, Direct Connect, and a Direct Connect variant known as Direct Connect plus VPN. Going to talk about Cloud Hub, a software VPN option, and also what a transit VPC is. Now, a managed VPN is just about the simplest way that you can securely connect your on-premise network to AWS. It's an AWS managed IPsec VP connection that you just use over your current existing internet connection. And when you would use this, generally you want a quick and usually pretty simple way to establish a secured tunnel connection. And some people use it as a redundant link for their direct connect connection. Now on the plus side, it supports static routes or BGP peering and routing. But the downside is it's dependent on your internet connection. So if you have a unreliable internet connection, then your connection to AWS is going to be the same. Now let's see how we set one up. First of all, we got to figure out what we're going to use on the customer side to be the endpoint for the VPC connection. Usually this is a gateway or a router. Then on the AWS side, we create a virtual private gateway and a VPN connection so that we can have something to connect to our on-prem gateway. And a nifty feature of AWS is it can auto-generate config files for popular routers like Cisco, Juniper, and Palo Alto. Then we can take that information or that config file and configure the gateway on our on-prem router such that it can connect to the VPN connection on AWS. And generally, we're using IPsec as the encryption protocol. And then finally, if it's an on-demand connection, we have to generate some traffic to force that connection to get established, and then we can go ahead and use it. Then optionally, we can configure BGP routing if we need it. Here's another look where we set up dual connections. And this is useful if you wanted to have a redundant connection into AWS, but you're going to have to take care of the failover on your side of the network. Let's take a look at Direct Connect. Now, Direct Connect is just a dedicated network over private data lines that's straight into AWS's backbone network. And companies use this when they need a really big pipe into AWS, or they want to be sure that they have a consistent experience as far as bandwidth. Now, on the plus side, it's more predictable than just using an internet connection, and you can get speeds up to 10 gigabits. Now, on the downside, it may require additional telecom and hosting provider relationships, and if you don't have a network circuit, then you're going to have to install one. Setting up Direct Connect is not something you do overnight. It usually takes some time. You're usually working with your data networking provider. Then once you have your network physically connected, you can create virtual interfaces and connect those to your VPCs, as in a private VIF, or you can connect it to other AWS public services. That's known as a public VIF. Here's what that architecture would look like. Now, granted, this is greatly simplified. Generally speaking, companies have way more complex wide area networks than this one. Now note that Direct Connect consists of a single connection between a customer's router and the AWS router, and it's not redundant. So AWS recommends that you're going to set up some sort of second connection. It can be a VPN connection or a second Direct Connect connection. Now, if you do have multiple ports of the same direct connection location, they will be provisioned on different routers. But that still gives you a single point of failure, so you should cover your bases and have a secondary connection, ideally through a secondary datacom provider. Now, there's a variation of Direct Connect that just employs a VPN connection, and this is just simply IPsec VPN over private lines. And the use case here is if you just want an additional layer of encrypted security over your Direct Connect lines. Now, when would I want to use this? Well, let's say that I'm part of a large conglomeration of companies, and while we're all owned by the same umbrella company, maybe we need to keep segregation between those companies and keep the data secret. So the umbrella company can arrange for a connection into AWS, and then all the subsidiary companies can use that same connection, only they're using IPsec to secure their individual part of that connection. Now on the plus side, it's more secure than just plain old Direct Connect alone, but it also adds an additional layer of complexity with the VPN component in there. And again, you would probably work with your existing data networking partner to set up a Direct Connect, and then you would go through the same process as if you're setting up just a VPN, but only you're using your private network. And here's how that looks. Basically the same picture, but we're just securing the traffic between the on-premise systems and the AWS Direct Connect location. Now we also have a VPN Cloud Hub. Now, this is kind of like a do-it-yourself MPLS network using public internet and IPsec VPN. And the concept is you're connecting locations in a sort of hub and spoke manner using AWS's virtual private gateway is the hub. This is good if you wanted to network a collection of remote offices. Now on the upside, it reuses the existing internet connection, so it's fairly simple to set up. And it also supports BGP routes. That's useful if you have, for example, an existing MPLS network and then using Cloud Hub VPN as a backup. Now, of course, it's dependent on your existing internet connection, and there's no real inherent redundancy in this connection type. You can set it up by assigning multiple customer gateways to a virtual private gateway and give each their own BGP ASN and unique IP range. And here's how this would look. Now, the communication from customer network to customer network really doesn't go directly. It routes to the virtual private gateway, then goes back down the VPN connection to that other customer network. Now, software VPN is kind of the ultimate do-it-yourself option for VPN. You provide your own VPN endpoint and your own software. An example of this might be if you want to use OpenVPN. It's not supported by the AWS VPN gateway. So you'd need to install the server portion on an EC2 instance within your VPC and configure clients to connect it. Using this option, you get ultimate flexibility and manageability, but you really have to design for any sort of needed redundancy, and you're on your own as far as support. Now, there are VPN software options in the marketplace as an appliance, or you can just spin up an EC2 instance and install your own. And here's how a network would look if it's using OpenVPN, for example. So we have the customer network, and we maybe have some mobile OpenVPN clients. They're attaching through a public internet gateway to our OpenVPN server, and then that then allows them to connect to our private subnet and the respective EC2 instances there. Now we also have a transit VPC, and this is a common strategy if you have geographically dispersed VPCs and locations all over the world, and you want to create kind of a common transit center, a common meeting place where all paths cross. Now the heart of this option is that you have one VPC that's really just a pass-through, and it's a good way to support a hybrid deployment across several different cloud providers. You get a lot of flexibility with this setup, but you also have a portion that's AWS managed, so you don't have to worry about it. But you do have to design for additional redundancy across the whole chain. Now, providers like Cisco, Juniper Networks, Riverbed, they have offerings that work specifically with their equipment and this concept of a transit VPC on AWS. And here's what a transit VPC might look like. You can see it's just a hub. It's very similar to maybe a public transportation transit center where all the buses or trains come to one point, and that's when travelers can get off one bus, get on another train, and so forth. And you can see we've also included here other cloud providers. So if your company is connected with AWS, but is also a Microsoft Azure customer, for example, this is a way where you can connect those two resources and have secure access. Now we're going to talk about a few VPC to VPC connectivity options. And really there's a lot of overlap with what we just talked about on the on-premise to VPC connection, but there are two unique ones here. One's called VPC peering, the other is called AWS Private Link, and we're going to talk about those two specifically. Now VPC peering is just a way to link two VPCs together so that they can communicate with one another. And that's when you'd use it, when you have multiple VPCs and they need to communicate or share resources. Now this option uses the AWS backbone without touching the internet. And that's a good thing because you don't necessarily want to have to egress out to the internet just to get to another VPC in your account. Now an important thing here is transitive peering is not supported. So in other words, if VPC A is connected to VPC B and VPC B is connected to VPC C, then A cannot talk to C through B. This just means that you have to intentionally peer certain VPCs if you want them to communicate. How you do this is pretty simple. The originator has to make a VPC peering request, then the acceptor accepts it. Then after the acceptor accepts it, both sides have to set up an appropriate route to route traffic to their other respective VPC. And here's how this might look. It's just two VPCs able to communicate to one another through this peering connection feature. We also have Private Link, and it's a way that we can connect to services, either AWS services or maybe services created by third parties, Now we can do that in a secure fashion right over the AWS provided network. Let's also say that maybe I'm a service provider and I have a set of APIs that I want to provide access to my subscribers. So I can create endpoints inside AWS. And then when another company signs up for access to that API, I can give them that endpoint. Then they can connect their VPC to it and make use of my API. So it's a bit different than VPC peering, where you're connecting two whole networks together. This is more granular. This is exposing services or connecting to services. And we call those services endpoints, VPC endpoints. And so the benefit is that it's redundant and it uses the AWS backbone. We don't have to go out to the internet only to loop back around to get access to the AWS service. And it's really easy to create a VPC endpoint or make use of a VPC endpoint. You can do that straight from the VPC console or the CLI. One thing to know about endpoints is that there are two types of endpoints. One is an interface endpoint and one is a gateway endpoint. And at least right now, there's only two services that use the gateway endpoint, and that's S3 and DynamoDB. Most all the other services that you can access via endpoints use interface endpoints. And the real difference here is on the interface endpoints, they're implemented as an elastic network interface inside your VPC or attached to your VPC. AWS attaches a private hosted zone from Route 53 to your VPC whenever you spin up one of these interface endpoints, and it uses kind of DNS redirection or DNS trickery to route any calls to those services to the private path. Now, in contrast, on the gateway side, the gateway uses prefix lists. That's just a predefined list of all the IP addresses that comprise that service. And it acts as kind of an intercept. You put it in your route table, or AWS automatically puts it in your route table. And it redirects traffic when you're trying to go to a certain IP address, like the S3 service, for example. It's going to intercept that and direct that through a private interface so that it doesn't go out to the public internet. Now, another main difference between the two different types of endpoints is how you can secure them. Interface endpoints use security groups, and security groups are just like the security groups that you use in normal VPCs or assigned to instances. Now, gateway endpoints use something called VPC endpoint policies, and they use the same syntax as an IAM policy, and you can define certain conditions in that policy. And where I would use VPC endpoint policies is if I wanted to control access to my S3 bucket or DynamoDB table and only allow it to be accessed when traffic comes through this VPC endpoint. And that's a good way to implement some least privilege principles on your S3 buckets in DynamoDB if you don't need to access them from outside of VPC. So we have our EC2 instances, and through an endpoint, we can directly connect to S3 without having to go all the way around out to the public internet, only to connect to the public side of S3. We can connect to the private side of S3. On a cloudy Wednesday night, October 29th, 1969, programming student Charlie Klein was sitting in front of a terminal similar to this one on the campus of UCLA, making notes in his work log. At 10:30 p.m., Charlie made history for being the first person to send a message over what we now call the internet. Charlie typed in the words login and waited eagerly as the message was transmitted. Well, as luck would have it, the system crashed after only the first two letters were transmitted. About an hour later, the offending code that caused the crash was fixed and the full login was transmitted. So, the very first messages sent over the internet will always remain low. Speaking of internet, we're going to talk about the different ways we can provide internet access to our VPCs. We're going to talk about internet gateway, egress-only internet gateway, and the NAT options that we have. Now, internet gateway is a horizontally scaled, redundant, and it's highly available, and it allows your VPC to communicate with the internet. Now, there are no availability risks because it's redundant, and there's no bandwidth constraints. And if your subnet is associated with a route to the internet, then it's a public subnet. And Internet Gateway supports both IPv4 and IPv6. Now, it fulfills two purposes. The first is it provides a route table target for internet-bound traffic. And purpose number 2 is it performs NAT for instances with public IP addresses. Now for purpose number 2, there's an important distinction here. Inside your VPC, all instances are known to each other by their private IP address. Their public IP address, if assigned, comes in only when they're trying to access the internet or being accessed from the internet. An instance that only has a private IP assigned, regardless of whether it has a route to the internet gateway, cannot get access to the internet. So the takeaway here is the internet gateway does not perform NAT for instances with private IPs only. So egress-only internet gateway exists only for one reason, for IPv6, because on AWS, IPv6 addresses are globally unique, and therefore they're public by default. In comparison, IPv4 addresses have a private range assigned by RFC 1918, and as such, they can't be accessed from the public internet. For IPv6, though, you don't need to use a NAT instance for private or public conversations, but you do need an internet gateway or an egress-only gateway to the internet. Now, the difference between an internet gateway and an egress-only gateway is that the egress-only gateway is only outbound. It prevents inbound access to those IPv6 instances. It is stateful, meaning that it keeps up with the connections and it forwards traffic from the instance to the internet and then back. Just like a normal internet gateway, you're going to have to create a custom route to route the egress-only traffic to that egress-only gateway. And this is what you'd use for IPv6 instead of a NAT instance, like you would for IPv4. Then we have the NAT instance. Now the NAT instance is just an EC2 instance that's running a special version of a Amazon Linux AMI. And its only purpose in life is to translate traffic from many private IP instances into a single public IP instance and back. And it doesn't allow any public internet initiated connections into those private instances. Now it doesn't support IPv6, that's where egress-only gateway comes in. And the NAT instance must live on a public subnet, and it has to have a route to the internet itself. To make use of that NAT instance, you're going to have to create a default route in your private subnet to provide a path for your private instances to get to it. We also have the NAT gateway. Now this is a fully managed NAT service, and it really replaces the need for a NAT instance on EC2. And it must be created in a public subnet, and it uses Elastic IP for its public IP address. And just like a NAT instance, you have to set up a default route to that NAT gateway. It's created in a specific AZ and it has redundancy within that zone. Now, if you want multi-AZ redundancy, you can create NAT gateways in each AZ and create localized routes for the private subnets in those respective AZs to go to their own AZ version. There is a limitation on bandwidth here. AWS guarantees 5 gigabits of bandwidth, but you can scale up to 45 gigabits. Now you can't use the NAT gateway to access VPC peering, VPN connections, or direct connect connections. So you're going to have to be sure to include specific routes to those networks in your route table. And remember, the most specific route in your route table is the one that gets selected first. Let's take a look at the comparison between a NAT instance and a NAT gateway. And this is relevant for the exam because you'll probably get a few questions on this. So as far as availability, the NAT gateway is naturally the better option for availability. For a NAT instance, you're going to have to architect your own high availability solution. For bandwidth, the NAT gateway can support up to 45 gigabits. The NAT instance is really dependent on what sort of instance you provision it. For maintenance, the NAT gateway is managed by AWS. And for the NAT instance, you're on your own again. So as far as performance, the NAT gateway is really optimized for network address translation. The NAT instance really is just a conscripted Amazon Linux AMI that's configured to perform NAT. Now the NAT gateway's public IP is an elastic IP that cannot be detached once you create that gateway. Now with an instance, you have flexibility where you can detach and attach other elastic IPs. You can't associate a security group with a NAT gateway, but you can with a NAT instance. And you can also use a NAT instance as a bastion server if you'd like, because it really is just a little Linux system. Overall, AWS recommends using a NAT gateway over a NAT instance because it's scalable, it's highly available, and it's fully managed. Now, when we talk routing, AWS, there's certain contexts that AWS uses the word routing in. And right now we're going to talk about the VPC context. So we're going to talk about route tables and something called a border gateway protocol. So you should already have an understanding about what routing tables are, that every VPC has an implicit router and it has a main routing table, and you can modify that main routing table or you can create new route tables. Now each route table has a local route for the CEDR block that's assigned to that VPC. And an important thing to remember here is the most specific route wins. Let's take a look at some examples. This could be a standard routing table. You see your 10.0.0.0/16. That's your CEDR assigned to the VPC. That's your local route. Then we have a 192.168 network that's going to a VPC or a VPN gateway. Then we have our default route to our NAT gateway. And I wanted to bring your attention to the prefix list that's on our route table there at the bottom. Now this entry is set up when you create an endpoint for your VPC. And if you remember endpoints, these are the private link network things, and it can be for an AWS service or it can be from a marketplace partner. And this prefix list is just a predefined mapping of all the IP addresses for that particular service. So it kind of acts as a sort of intercept to route the traffic that would normally go out through the default route, in this case, the public internet. And it just routes it through this VPC endpoint connection, which rides on the AWS network. So let's take a look at some addresses and see where they would route us. So if we need the destination 10.0.45.34, well, that's in our local CEDR, and so that's just going to route via our local target. 64.56.34.1, well, that doesn't meet anything else on our list, so it's going to fall under the default route, and so it's going to go out our NAT gateway. We have 192.168.0.7, and that falls within the VPN gateway route. Now, if we try to go to S3 from this VPC, because we're using a VPC endpoint, that prefix list is going to intercept those requests and route those through that VPC endpoint. And as an aside, our EC2 instances are going to talk to that VPC endpoint using their private address. Now, how about this one, 10.0.255.255? Well, that's a trick question. The 255.255 is a broadcast address for our /16 subnet. And if you recall, VPCs don't support broadcast, so this guy's going nowhere. Now, if you know a bit about networking, you might have heard of some routing protocols like RIP or OSPF, or maybe even BGP, Border Gateway Protocol. Border Gateway Protocol is really popular on the internet, and it propagates information about the network and allows for dynamic routing. Dynamic routing meaning that I can choose different paths depending on the availability or the weight of a certain path. It's required for Direct Connect, but optional for VPNs. And the alternative of not using BGP is just setting up static routes. And AWS supports BGP community tagging as a way of controlling the traffic and the scope, and some large enterprise networks need that. Now, BGP is a little bit different than other routing protocols. Well, BGP runs on TCP, port 179, so that needs to be open. And it also needs some ephemeral ports. Remember these guys? Now there's this thing called Autonomous System Number, or ASN, and that uniquely identifies each endpoint in a BGP network. And you can assign different weights to routes in that network, and the higher weight is the preferred path for outbound traffic. So here's an example of where we have two paths to AWS from our corporate data center. We have a VPN connection, and we have a Direct Connect connection. So let's say we wanted to cut over to the Direct Connect connection. All we do is specify a higher weight to the Direct Connect connection, and then our router would take care of transitioning the traffic from the VPN connection over to our Direct Connect. Now, keep in mind, we're still keeping the VPN connection in our routes, but we're giving it a weight of 100. So under normal conditions, it's not going to get any traffic, but it kind of serves as a backup. So if our Direct Connect goes down, then our traffic's just going to automatically route over our VPN connection. We're going to talk a little bit about some enhanced networking features that AWS offers. And generally, the use cases for these are high performance computing, where you have a lot of data or a lot of very powerful computing resources that need to communicate at a high rate of speed. And specifically, AWS offers some specialized network interfaces or virtualized network interfaces that use some special techniques and special processes to enable way higher performance than traditional virtualized network interfaces. To make use of these, you may have to install some additional drivers if you're not using Amazon Linux AMIs. And there's two main ones here is the Intel 82599 virtual interface that tops out at 10 gigabits and the Amazon Elastic Network Adapter that tops out at 25 gigabits. And which interface you can use depends on which instance type you have. Now, you probably won't be asked on the exam which instance types use which network adapters, but just be aware there are two variants out there. I wanted to introduce you to a concept that's relevant for the networking chapter, and that's called placement groups. The idea behind placement groups is we have some control over how we can arrange our instances over the physical hardware that they live on. And AWS has three different types of placement groups. The first being clustered, we have spread, and we also have partition placement groups. And I'll go over each one of these and tell you a little bit about the pros and cons. Now, when we're talking about clustered placement groups, we're talking about grouping your instances close together, generally on the same rack or the same hardware, so that they can have the lowest latency between their communication. Now, in contrast with spread placement groups, we can put our instances on physically separate hardware. So if we're concerned that if a rack fails or a piece of hardware fails on that rack, then it doesn't necessarily take down our whole system because we have some diversity on where that instance lives. Now, a relatively new placement group that's been released is something called partition placement groups. And we'll see some examples of how this differs from a spread placement group in a little bit. But for now, you have the ability to group your instances and then spread those instance groups across different collections of hardware. Now, when might I use a clustered group? Well, if I have applications that really benefit from very low latency communicating between the instances, then I probably want to use a clustered placement group. Now, in contrast with spread placement groups, let's say that I don't necessarily want to have all my instances on the same physical hardware rack in case that rack has a problem. So I can spread my instances across different physical racks. And for partition placement groups, if I have a really large application that consists of a lot of instances, then I can group those different layers and different partitions and manage how those partitions are spread across different hardware. Now, the benefit of a clustered placement group is that we can benefit from some enhanced networking throughput and a very low latency. The downside is that clustered placement groups have a finite capacity. There's only so much that you're going to be able to jam onto one physical rack. So it's generally recommended that if you're going to make use of a clustered placement group, go ahead and provision all the instances that you need up front, because it may be very difficult to add an instance to that clustered placement group later down the road because maybe there's no capacity. Now, the benefit of a spread placement group is that I can put my instances across multiple AZs, and the spread placement group is going to be sure to enforce that for me. The downside is that I can only have a maximum of 7 instances running per group per AZ. Now, as far as partition placement groups, the benefit there is it's really designed for large multi-instance architectures, and we'll see an example of this in a bit. But as you'll see in a bit too, it doesn't support dedicated hosts. And that makes sense if you think about it, because if you're just putting everything on a dedicated host, you might as well be using a clustered placement group. So let's look at some visual examples. I think that may help reinforce some of these concepts. So by default, AWS will just allocate space for your virtual instances on whatever rack and whatever physical machine it can use, it tries to spread this equally. And let's say that maybe you have an application that you want those instances to be very close together. And so you would use a clustered placement group. In this example, we have VMs 1, 2, and 3 that all happen to be on the same rack. Let's say we are concerned about a physical machine failing or maybe a rack failing. We would use a spread placement group to get some diversity on what systems are actually hosting our VMs. Now, partition placement groups are sort of the evolution of spread placement groups. Let's say you have a pretty large distributed application that has maybe 50 underlying instances. By using a spread placement group, each instance would be theoretically placed on its own set of unique hardware. And this gets really kind of crazy if we're thinking about, maybe 100 or 500 instances out there. And so rather, we can group instances into logical partitions and have those placed on separate racks. And we still have the resiliency because our application inherently can deal with those nodes going offline, but we still have the benefit of hardware diversity. And so, for example, in our distributed application, in this case, it's a Hadoop HDFS landscape, we can tolerate having VMs go offline. That particular landscape is tolerant of machines coming in and out. But we also, by using partition placement groups, we are able to still have some benefit of hardware diversity. Now, still talking about routing, in this case, we're going to talk about Route 53. And you should already know about Route 53. You should know what it does and what a DNS is, what the different types of DNS records are, Route 53 concepts like an alias or a hosted zone. And so a little bit of trivia here. Do you know why it's called Route 53? Well, it's because the DNS service port is 53. So Route 53 has multiple policies that we can use. And again, similarly how I've done in the past, I'm going to lay out the policy and then try to translate that into what Route 53 is thinking when it's trying to execute that policy. The first policy we have is just the simple policy, and it's simple. It's just we're creating an entry, a DNS entry, and Route 53 is saying, okay, here's the destination for that name. Then we have failover. And so Route 53 would be thinking, normally I'd route you to this primary place, but it appears that it's down based on my health checks. So I'm going to fail over to this other backup system and send you there instead. Then we have geolocation, and what Route 53 is thinking there is, hey, looks like you're in Europe, so I'm going to route you to a resource closer to you in that region. Then we have geoproximity, and it's different than geolocation. So Route 53 is thinking, hey, you're closer to US East 1 region than US West 2, so I'm going to route you to US East 1. Then we have latency, which says, let me see which resource has the lower latency from you, and then I'm going to direct you that way. Then we have multi-value answer, and this is where Route 53 can return several addresses. It's kind of like a sort of basic load balancer. Then we have the weighted policy. And Route 53 allows us to set up multiple resources, and we can assign a weight, and it will distribute the traffic based on that weight. Let's take a look at each type and see what the behavior is when we issue a dig command, for example. So here I'm just creating a basic simple route policy, and I'm pointing it to an IP address. And as you can see, it's returning the address 52.11.7.197. Pretty simple. Now I'm going to set up failover routing. So I'm going to create a record with the same name, but different IP addresses. And I'm going to say that it's a failover of a primary and then a failover of a secondary. And I'm going to have a health check associated with the primary. What I've done prior is set up that health check. And really all it does is just pings and tries to hit my primary resource. And if that's unavailable, then it's going to send me to the secondary route or the secondary resource, which in this case is 120.13. So here's what it looks like. Before I stopped my primary instance, it was sending me to the 197 address. And then after I stopped the instance, it sent me to the 113 instance, which is exactly the behavior we were looking for. And now for geolocation routing. So I can configure a route for North American users, for example, here on the left-hand side. And then I can also configure a default route for everyone else. Now, special note here, it's important that you have a default route for geolocation because sometimes Route 53 won't be able to determine where the person's coming from. And so the default route is kind of the catch-all. And you can see this time I'm using a CNAME, so I just wanted to demonstrate that we can indeed use many different types of DNS records. So on the top, I'm in a system that's in the USA, and I'm going to issue my NSLOOKUP command, and it's going to show me the IP address 120.113, and it resolves to US East 1. Now on the bottom, I'm on a machine that's in Germany, and using the same command for the same name, it's directing me to a different IP address. For geoproximity, I'm not going to show you a screenshot since it would be hard to see, but here's the concept of geoproximity. Let's say we have US West 2 and US East 1, and let's say somebody lives in the little yellow marker there. That's probably about St. Louis. So let's say that we're distributing traffic across two regions based on location. And those closest to one region would go to that region. So in our example, the requester at the yellow map marker would route to the US East 1 resources. But let's say that we wanted to shift more geography to one region. We can change the bias on the geoproximity record, and that has the effect of increasing or decreasing a radius around which we route traffic. And the bias can be between -99 to +99. And a positive bias will increase our circle, and a negative bias will decrease our circle. And in our case here, the yellow marker would route to US West 2 resources because it's now within the positive bias circle of US West 2. So why would I want to do this? Well, let's say that using proximity, my US East 1 resources are maxed out just due to the larger population on the east side of the country. Adjusting the bias would allow me to more equally distribute the load across my regions. Now, latency-based routing is when we can route based on, well, latency. So in this case, we have two records. We have a record that's set up to serve when latency is lower to the US East data center. And then we have one that's set up to serve when latency is lower to EU Central. So this is different than geolocation because it's not really based on geography. Rather, it's based on the latency between that requester and ultimately the data center. So we can see this in practice. If I log in into a machine in the USA, I'm going to get directed to US East 1. And then if I happen to be logged into a machine in France, for example, where presumably the latency between that machine and EU Central 1 is going to be less than the latency between US East 1, it's going to direct me to the European system, in which case it did. Now, multi-value answer routing is useful when you want to have the same name pointing to multiple IP addresses. And you can also set up health checks so that only healthy endpoints would be served. And this is kind of a very basic load balancing or round robin type direction of traffic. So in this case, if I use my NSLOOKUP command, I'm getting back multiple IP addresses, and I can choose any one of those IP addresses. Now, if I happen to try to visit one of those IP addresses and it comes up dead or unresponsive, then my client's automatically going to just reach out for the next IP address. Now we have weighted routing. In this case, we have two records with the same DNS name. One is going to US East 1 and one is going to EU Central 1. And you can see the weight is 10. It matches. And so what this will do is this will route traffic equally to both of those destinations. Now weight numbers can be anywhere from 0 all the way up to 255. And if I set it to 0, then that has the effect of disabling traffic going to that endpoint. So here, if I execute my NSLOOKUP command, I have an equal chance of getting either endpoint. The formula for weighting is pretty simple. It's the sum of all weights is the denominator, and the numerator is the weight for a specific record. So that's going to define what percentage of traffic goes to what destination. So let's look at that in terms of some examples. So if we have weight for endpoint 1 as 10 and endpoint 2 as 10, well then each endpoint is going to get 50% of the traffic. Now if I set the weight for endpoint 1 as 0 and endpoint 2 can be anything, it can be 1, it can be 255, whatever. As long as endpoint 1 is 0, then endpoint 2 is going to take on 100% of the traffic. And this is a common way to transition traffic away from certain instances that you maybe want to take offline, like maybe through a blue-green deployment where you might want to gradually meter the traffic across your instances. Let's talk a little bit about CloudFront. Well, you probably already know that it's a distributed content delivery system, and it can handle anything from just simple static assets all the way up to 4K live streaming. You should already know how to create a CloudFront distribution and understand the edge location concept. And know that it's also integrated with the Amazon Certificate Manager service and also supports SNI. We're going to get into some specifics around networking. Specifically, we're going to talk about SNI and SSL. So if you've set up a CloudFront distribution, you probably faced a screen similar to this, and it has SSL, custom certificates, options for SNI, TLS, lots of acronyms. So I wanted to spend some time and really dive a little deeper on these concepts so that you truly understand what you're doing when you're configuring these things versus just picking options. So SSL and TLS, they go back quite a ways. SSL is actually the forerunner of TLS. TLS is really considered kind of the current standard. And you want to be sure that you can support TLS version 1.2. And in some cases, you want to actually disable prior versions of SSL because they had security flaws. And a lot of times when people are talking about SSL or TLS, they're used interchangeably. And I'll probably use SSL and TLS interchangeably, but what I really mean is TLS. Now we can use the default CloudFront cert, but if we want to serve up our own content using a custom domain, we have to use our own custom SSL certificate. Now we can generate this certificate using the AWS Certificate Manager, or we can purchase one from a third-party issuer and upload it into IAM. Now notice here that I'm using an SSL cert with a wildcard at the front. And that cert will be good for any subdomain that I want to add on, like www.scottpletcher.guru or cdn.scottpletcher.guru. Now, if I do choose to use my own custom domain and I've selected my custom SSL certificates, there's one issue. One of SSL's main functions is to guarantee that the website that I'm visiting is legitimate and it's the correct website in the certificate. It does this by making sure the domain name of the server matches the cert. Otherwise, you'll get a warning in your browser like this. Since CloudFront is a shared service, the host machines behind CloudFront will be serving up all sorts of content and all sorts of SSL certificates. And so to get around this, we have two options. The first is to pay for a dedicated IP address for each edge location. And this dedicated IP address will just serve up our content and use just our certificate. The second uses something called server name indication, or SNI. It allows the client to specify which host it's trying to connect to, and the server can present multiple certificates on the same IP. And so the client is asking for the correct certificate, and the server, CloudFront in this case, is presenting it. Now the downside of using SNI is that a few old browsers don't support it, but these are really oddball browsers like Opera Mobile for Symbian. All modern browsers have supported SNI for at least the past 5 years or so. Now the security policy is also important on CloudFront as well. And we can adjust what SSL and TLS versions our CloudFront distribution supports by choosing a security policy. You can see here that all policies support TLS 1.2. The default behavior for most modern browsers is to use the most modern protocol and then fall back as needed. But if we wanted to get super strict, we could specify TLS 1.2 version 2018 and only support TLS 1.2. All right, let's talk about elastic load balancers. The number one function of load balancers is to distribute inbound connections to one or more backend endpoints. And AWS has three different load balancers that we can use. First being an application load balancer, the next being a network load balancer, and it also has a classic load balancer. And it kind of discourages you from using the classic load balancer, but they keep it out there because there are certain customers who still want to use it. And the difference between these load balancers is the application load balancer generally works on layer 7. And if you recall from our OSI model lesson, layer 7 is the application layer, hence why it's called an application load balancer. And it generally deals with HTTP and HTTPS, while the network load balancer operates on layer 4, which is the TCP level. Now we can use load balancers either facing the internet in a public way, or we can use them internally inside our VPCs to distribute internal workloads. And also load balancers are auto scaling, hence the elastic part. And as they scale, they're going to consume IP addresses within your VPC subnet. So you should make sure that you have plenty of spare addresses, especially remembering there are certain reserved addresses that you're just not going to be able to use. And if you run out of addresses inside a VPC subnet, then you could run into problems with scaling. Now, the different types of load balancers have some similarities, but they also have some differences. And on the exam, you're going to need to know a little bit about some of those similarities and differences. So first, let's look at the similarities. So all the load balancers have zonal failover, meaning that if an AZ goes down, they're going to fail over to another functioning AZ. Now, application and network load balancers can only work inside a VPC, whereas back in the olden days when there was really no concept of a VPC, that was called EC2 Classic. The classic load balancer can still work in EC2 Classic, but as I said before, AWS really discourages this. And if you're building any sort of forward-looking architecture, be sure you're using VPCs, and therefore you really would have no need to use Classic. You can either use an ALB or an NLB. Now, all the load balancers have health checks, and they can balance loads across zone. They also have plenty of CloudWatch metrics, and they can also now terminate SSL connections. Previously, only application load balancer could terminate those connections, but now the NLB has TLS support, so it can now do those terminations as well. And all the load balancers have resource-based IAM permissions, so you can define certain IAM permissions for users and roles and resources that can access or do stuff to those load balancers. Now here's a comparison chart of the differences. It's not a full exhaustive list of all the features, but I just pulled out some where there are definitely differences between the different load balancers. And I'll call your attention to a few of these items that seem to appear commonly on the exam. And note the protocols here. The application load balancer works at layer 7. That's HTTP and HTTPS. While the network load balancer works at a lower level, layer 4, and it makes use of TCP, UDP, and TLS. Now, as far as routing options, and this means how you can control the flow of traffic to your backend servers. At level 4, where the network load balancers are, we don't have much available. Basically, we can route based on the source port. So we can route traffic to instance 1 if that request comes in on port 81, or instance 2 if the request comes in on port 82. But for TCP, because that's a connection-oriented protocol, once a routing from a client has been made to a backend host, that routing is persisted for the duration of the connection. Now, ALBs, on the other hand, have lots of options for routing. We can route based on the domain host name given or the path given in the URL. We'll see an example of this in a bit. And we can route based on HTTP header elements, HTTP method options like post, put, and get. And we can even route based on the source IP and a query string parameter inside the URL. Lots of flexibility here. Application load balancers work at a higher level. It works at the application layer. So it can do some pretty interesting things. Like one of the features is path-based routing. So based on the URL path included by the client, we can direct that load to one of many different target groups. So in this case, if we have login.acme.com/customer, we can direct that to a set of servers for the customer web fleet target group. Now, network load balancers, on the other hand, they really excel at speed. If you just need raw speed and throughput, then you probably want to use a network load balancer. And you can use a network load balancer to direct HTTP and HTTPS traffic. So in this scenario, let's say we have a client that uses SCP to copy files or upload files. And so we're using the network load balancer to distribute the work across a target group of worker instances. They will take that file, maybe they run some processing on it to extract some metadata. And in this case, let's just say they're updating DynamoDB. Now, sticky sessions are an important feature for web applications. Most web applications keep up with clients using session IDs. And this is a way to uniquely identify the client for stuff like shopping carts and session parameters. If I just direct the client to whatever web server has less load, then I take a chance of landing that client on a web server that doesn't have the session variables that maybe a previous connection used. So enabling sticky sessions is how the ELB can keep track of the client and which web server it handed it off to, so it can keep sending it back to that same web server, thus allowing continuity for the client and the web server. Here are some of my exam tips. You really should know the pros and cons of each on-prem to AWS connection mode. And you need to know the functionality of the different VPC components, like a customer gateway, a virtual private gateway, and where they go and how they fit together. You should know that Direct Connect is not inherently redundant, but you should also know how to architect a network that is redundant. For instance, you can use VPN or a secondary Direct Connect. Now, multicast and broadcast aren't supported in VPCs, and you know the reason why now, because they're a layer 2 item. Now, I will say that some AWS engineers have come up with a proof of concept that allows multicast on layer 3, thus enabling VPCs to kind of support multicast, but it's not supported. And for the purposes of the exam, just know that multicast and broadcast aren't supported. You should know what's meant by stateless and stateful and connectionless and connection-based in terms of IP protocols. You should know what ephemeral ports are and why they might be needed in a NACL or an SG. For routing, you should understand BGP and how to use weighting to shift network traffic around, and know how routes in a routing table are prioritized, and it's the most specific is first. And what other routing protocols does AWS support? None. Only BGP. Your only other choice there is static routes. For VPC peering, just know that your CEDAR ranges cannot overlap. And after the VPC owner accepts the peering request, routes must be added to the respective route tables. Now, transitive peering is not supported, but mesh and hub and spoke architectures are with the proper NACLs and routes. But a transit VPC is supported. Now, for internet gateways, you should know the difference between a NAT instance and a NAT gateway. Know that an internet gateway is horizontally scaled and it's redundant and there's no bandwidth constraints. Now, NATs do have bandwidth constraints, but VPCs can have multiple NATs across AZs and subnets for scale, so long as routes are properly defined. And you only use an egress-only gateway for IPv6. For Route 53, you're going to have to understand the different types of routing policies and the use cases. You should know the weighted routing formula. And remember that Route 53 is a global service. For CloudFront, you should understand what must happen to set up a custom domain within CloudFront, and understand what SNI enables and what it does, and the necessary alternative. For Elastic Load Balancer, you should know the 3 different types of load balancers and at which OSI layer they work. Understand which major features each deliver by way of protocol, SNI, sticky sessions, and know what sticky sessions are and when they come into play. Remember to read through the white papers that I've linked in this lesson. If you're watching on a browser, they're going to be over here, and if you're watching on a mobile device, they're going to be down here when you put the device in portrait mode. Now, on the surface, Direct Connect may seem like a really complex and way costlier way to connect to AWS, but I encourage you to do some financial analysis because if you're transferring a lot of data, then it might be more cost effective than you think. I like to get into a practice of explicitly denying as much traffic as I can with my NACLs and SGs, really following that principle of least privileges. And there's certain services out there which you should just get in the practice of denying, like TFTP or Telnet, if you don't need them. The idea is you want to make your internet-facing attack surface as small as possible. I encourage you to really spend some time to think out your VPC layout. It can quickly become an unmanageable mess otherwise. And I recommend watching this 2017 reInvent video for some good advice. Now you can use Route 53 for your domain even if AWS isn't your registrar. You just have to update your DNS entries with your registrar to use the AWS ones assigned when you created your hosted zone. Not only do ELBs spread load, they also provide a very useful layer of abstraction, easily enabling stuff like blue-green deployments or rolling updates. All right, so now it's time for the network design challenge number 1. The idea here is we present a question that's worded and constructed much like an exam question, and you should budget yourself about 2 minutes to read the question and come up with the answers. So once you see the question, pause the video, give yourself 2 minutes. Then when you have the answer, resume the video and I'll explain what the answers are and the whys and why nots. Get ready because here comes the question. Okay, welcome back. Hopefully you've managed to formulate an answer. The question posed here was a bit of speculation on our part, but this is very representative of exam questions, and this is actually representative of real life situations where you have to somewhat speculate on what could be the problems to help focus your efforts. So if we look at the question, we have two main pieces here that we want to pay attention to. One is that the connectivity between VPC A and D is slower than they want it to be. So it doesn't say that it's non-existent. It's just slower than they want it to be. Now, slow is a relative term, but let's set that aside for now. And we're asked to select some valid reasons that might explain this situation. So we have to choose 3. So what we can do is we'll go up to the top here and we'll start with A. And it says they forgot to turn on enhanced peering mode on one of their VPCs. Well, there's no such thing as advanced peering mode, so we can eliminate that one straight away. For B, transitive peering is not supported, so they must restructure their connections to not require it. Well, it's true that transitive peering isn't supported natively by AWS, but that doesn't explain slowness because if it wasn't supported, then they wouldn't have any connectivity, but at least they have slow connectivity. So we can eliminate that one. C says the regions containing VPC A and D are physically too far apart to meet their expectations. Well, that's a perfectly valid reason why it might be slow. Maybe they put one VPC in one region, then VPC D on the other side of the earth, and the latency is just too much for either their liking or their application. So we like C. Let's move on to D. Although VPCs A and D are peered, the routing table in VPC A does not have an entry for VPC D's CEDAR block. Well, this is one of those all or nothing items. And if we didn't have a route in the routing table in A, then we wouldn't be able to reach D. But here it seems like we are able to reach it. It's just a little slower than they want. So option E is the internet gateway they attach in either VPC A or VPC D does not have enough bandwidth to handle the required data volume. If you recall, internet gateways do not have any real bandwidth limits that we would hit, so that's probably not a reasonable answer. So if we go on to F, they have configured a hub and spoke network via VPN where both VPC A and VPC D are connected via a route on their corporate network. So if they're routing traffic all the way back to their corporate network rather than routing through VPC peering, the speed between the two VPCs would then be limited by the speed of their connection to each VPC back to their corporate network. And if they have an undersized or maxed out internet connection, then the VPN connection speed would suffer as well. So that's a possibility. I like that answer. If we move on to G, they have reached their account limit on VPCs and must request a limit increase or reduce the number of VPCs. Again, this is one of those all or nothing items. Account limits are generally enforced when you try to create a new thing. So when I tried to create a new VPC, if I had reached my account limit, it would prohibit me from doing that. Choice H is they have enabled jumbo frames on their hosts inside their VPC. Now, some EC2 instances do support jumbo frames, but the standard Ethernet MTU is 1500, and jumbo frame traffic going outside of VPC will be fragmented, and fragmentation will tend to slow down traffic. So this is a plausible answer. So here are our answers, C, F, and H. So how do you do? All right, here we go with challenge question number 2. Same format as before. I'm going to present a question. Budget yourself about 2 minutes to answer it. Then I'll come back and we'll walk through the answers. And here comes the question. All right, welcome back. Hopefully you had some time to read over the question and formulate some answers. And you'll notice this question didn't necessarily say pick a certain number. I kind of left it open-ended because I wanted to talk through the different options here. Now on the exam, you're always going to have pick 1, pick 2, pick 3, something like that. You could have as many as 8 options and it says pick 4. And unless you get all 4 correct, then you're not going to get any points for that question. Hopefully you picked at least one. There could be some other ones that we want to talk through here as well. So there are 2 things that I look for in this question. Number 1, what's the real question being asked? And then secondly, what are the details that the question provides that seem like they would help guide me? So for this question, we're being asked what are some reasonable ways to distribute traffic over our newly scaled server fleet. And I also noticed that we're talking an e-commerce site. So e-commerce, that usually means that I want SSL support. And if there's any sort of cart functionality, a lot of times that uses sessions to keep up with the cart. So those are things starting to formulate how I want to approach this question. So if we start at the top there, Route 53 failover policy. Well, the failover policy is not really going to do me any good about distributing load across web servers. I'm going to discard that one. Now the Route 53 latency policy, that's really not going to help me either, because maybe all my users have the same latency. I mean, they're still going to go to the same place, and that's not going to help me spread load over multiple servers. Now, Route 53 multi-value answer policy, I remember that we can use that to return multiple IP addresses for one DNS name. And it does have the effect of a load balancer, sort of a round robin type load balancer. Now, the client's resolver may cache that IP address and just send it straight back to the same web server, but that's really risky. I can't rely on that. Although I could probably use this to spread load across my web servers, I think it has some other unintended consequences that are probably pretty negative. Well, CloudFront isn't an option for us because all it does is serve up content. It's not going to spread load. It's not going to spread inbound connections across my web servers, so I can discard that. So now I'm left with the 2 application load balancer options. And I know that I probably want to support sticky sessions and SSL. And if I look at the 2, I recall that application load balancers does indeed support sticky sessions, and it does support SSL. In fact, we could create an ELB app load balancer, front it with a SSL certificate that we created in Amazon Certificate Manager, and then add the new EC2 instances to the target group, and we'd have a really robust solution. So I like that answer best of all, and I think I'm going to stick with it. All right, welcome to the lab for networking, and we're going to call it Network Mess. Now, if you remember from our first chapter, we talked about this concept of choose your own adventure. If you want to push yourself, then you're going to go the expert path because I'm going to give you the least amount of instruction and hints that way. And if you're not quite there yet, I'll give you a few hints and you can go the intermediate route. And if you're just following along, you can go straight to Newbieville and just watch how I did it without trying anything. And I wouldn't really recommend this, but to each his own. So here's the scenario. As with most IT departments, your department is shorthanded, and especially when it comes to skilled AWS engineers and architects. Your manager hired a contractor, and his name is Sven LaFors, to do some work. In the interview, he seemed a little strange and offbeat, but people are quirky sometimes, and the best engineers are some of the quirkiest people I've met, so we're going to give him a chance. Turns out LaFors really didn't know what he was doing, and now we have to fix the mess that he created. So this is how we're going to do this. I want you to select a region that you don't normally use, and this is just because you're less likely to have a bunch of other resources in that region that may confuse things. So pick a faraway region. It's optional, but definitely recommended. And then you're going to execute a CloudFormation script, and this is going to build our website landscape, and hopefully it works perfectly. This is the pre-LaFors version of the landscape. And I want you to test out the website. It works. Make sure that you can get to this website. Make sure there's nothing else that's preventing you from getting to this website, and you can see it works. Then we're going to execute a CloudFormation script that's going to represent the mayhem that LaFors creates. In other words, the post-LaFors era. And you're going to have to figure out what LaFors did and fix it to be able to get your website back up and operational. Now, the CloudFormation scripts are on our GitHub for this particular course. I'm going to link them in the resources of this lab. And what you're going to be looking for is there's two files out there. There's a step 1 file, which is our creates the landscape, and then a step 2 file, which is our LaFors disaster. So you're going to execute the step 1, then I want you to go out there and test it. In the outputs, you're going to get a fully qualified domain name, and that's the domain name of the instance that it spun up to host this website. And you're going to put that in the browser, and you should get a web page that says, "Keep being awesome, Cloud Gurus." Then I want you to run the CloudFormation template that is for the LaFors disaster. And when that finishes, you're going to get the same fully qualified domain name, but you're going to see that LaFors was there, unfortunately. And you're going to try that website again, and it's going to be no worky for that website. Now, if you're getting off at the expert level, stop. Here's some rules. Do not use a change set. Do not look at the scripts. And do not look at the preview when you're updating, because those can all give you hints as to what changed. For maximum expert badassery, I want you to go in there just as blind as you would if this happened in a real situation. So go off and try it and then come back and you can watch the rest of the video and see a method that I use to resolve this situation. Okay, if you're sticking around for the intermediate level, I'm going to give you some hints here. So the first hint is I only touched the networking components. I didn't log into the EC2 instance and shut down the process. Number 2, create a change set when you're implementing this CloudFormation template. And that's exactly the purpose of a change set, is it gives you an idea of what impact it's going to have to a landscape before it actually executes it. So that'll give you some hints about what changed. And 3, remember the fill in the blank here, guys. So if you're intermediate level, stop the video right now and go give it a try. When you're done, come back, resume the video, and I'll show you how I did it. Okay, let's go through a walkthrough of how I step through the problems and resolve them. Okay, we're going to start from our AWS console, and then we're going to go under CloudFormation. We're going to create new stack, and then we're going to select the template for the setup. We're going to give it a name here. And I've also entered a few different instance types that should be available in all regions. You can pick which one. And we're just going to hit next, and eventually it's going to start building our resources. I'm going to pause right here and then restart when the resources have been built. Okay, the create is complete. If we go over to the outputs, we can see our fully qualified domain name of the instance that was created. I'm going to copy that and pull that up into a browser. And you can see our website works. In fact, we can see the instance. If we go out to EC2, we'll see a running instance, and it's just a normal running instance. If we go to VPCs, we can see that we've created a VPC. I'm going to filter by just that VPC. And you can see we've created a subnet, just a single subnet. This is a very simple network. We have an internet gateway, no egress. DHCP options are the same. We have one elastic IP that we're using. Now we can go back to CloudFormation and implement the LaForce disaster. I'm going to just update the stack. I'm going to choose the template that will create the havoc. And next, next, next. And your landscape will update. Now, it won't happen as fast as this because I sped it up. Probably within about maybe 3 or 4 minutes, you're going to get an output here. You can see LaForce was there. We try our fully qualified domain name, no worky. It's going to time out and just keep spinning. So now we got to figure out what the problem is. Well, the most obvious thing is our EC2 instance up and running? Yep, it's still up and running. Now, what I like to do is step inward. So I'll start with the furthest out resources and then step back into where the problem is. So we'll first look at our VPC. I'm going to filter by that VPC. And check out the subnet. Subnet's still there. They seem to look okay. The route tables. We did have 2 route tables before. If I look at this route table here, one thing that steps out at me is there's really no default route. It goes to 10.1.0.0. I need to change that. That should be a default route for everything going out to the internet gateway, or else the instances in that VPC can't reach the internet. Internet gateway looks okay. There's really not much you can do with that. DHCP options look okay. The elastic IP is still there. There's not much you can configure there. Now I can go down to my network ACLs. Okay, I see one ACL there that doesn't have any subnets associated with it. The inbound and outbound look okay. They're just basically allowing everything in and out, but there's no subnet associated to it. So if I go to my other network ACL, oh, UDP port 80, that doesn't seem right at all. Plus there's a rule 100 that denies everything. And here in the outbound rules, we're outbound port 80, but I'm missing the ephemerals. Now I can fix this pretty easily just by reassigning that subnet back to my default NACL. And I can delete this other one. Now I could have also edited that new NACL, but in this case, I'll just reassign. Now if I have a look at my security groups, let's take a look at the inbound rules. TCP port 80. Again, the source is 10.0.0. That's not going to let me access that from the internet. So I'm going to need to change that. I'm going to change that to allow anywhere to access this over port 80. Now let's go try our website. Voila, it works again. Thank goodness. We've undid the mess that LaForce created for us. Now we can tear everything down. That's pretty easy with CloudFormation. We can go out to the CloudFormation console, click it, do delete stack, and it's going to get rid of everything we created almost like we were never here.